All right, welcome everybody. Okay, this is the last session of the day. I just want to welcome Katie and Shawn. Shawn is online. We're hoping you can hear him loud enough through the owl, but we may need to speak up so he can hear us. That's all I have. I'm going to pass it on to Katie.
All right. Hi, everyone. Shawn, I can control the slides for you if you just want to tell me next. But
yeah, that works.
Okay. Sounds good. And we're going to shut the doors so everybody can hear you nice and clear.
Yeah, I can sort of see heads in the distance there. So I don't know how many are in the room, but
We've got a few, yeah.
All right.
Yes, for intro, I'm Katie Watkins-Brandt. I'm with NOAA. I'm the Section Chief of Science Services, and Shawn is online. I wish he could be here with us today. I'll let him introduce himself. But today we just wanted to go through the recommended practices for shipboard radiometers. We were both part of a paper that was recently published on best practices. So we're going to share some of that information today. Shawn's going to give the presentation and talk a little bit about background on radiometers, and then and talk about why this data is important. And then we're going to just showcase just a couple. I was going to show you how to clean them, but my isopropyl alcohol got confiscated at the airport. Apparently, you're not allowed to fuck out flammable liquid. I also got my knife confiscated. Like a rookie move, right? I'm like, oh, Katie, that was bad. So I lost both the knife and my flammables. They were like, I don't know if we're gonna let this lady fly. Like, should we even let her on the plane? Anyway. So I will show you just a couple of the models that we do have, some paranometers, and then go through the best practices in terms of maintenance, and we'll kind of go from there. So I will let Shawn introduce himself and kick off the presentation. Go for it, Shawn.
All right. Well, thank you, Katie, and hope you all can hear me. I'm sorry again that I'm not able to be there in person. I'm getting good at doing this remote training stuff. Yeah, I'm Shawn Smith. I'm at the Florida State University. Some of you know me as from the SAMOS project. I've been leading that project for a better part of 15 years. But I also am a co-PI on the R2R project. So very much been involved in this community for going on 25 years now, you know, in terms of getting data off the ships and working with you all. So yeah, go to the next one. Thanks, Katie. So yeah, just an acknowledgement. Again, this material, almost all of this was pulled from a best practice document that is now published in Frontiers Journal. It was lead authored by Laura Rihimaki at NOAA. And she also works with a project known as the Baseline Surface Radiation Network. I'm not sure if you've heard of this, but BSRN is a DOE-funded program to basically do high-quality radiation measurements from land stations. There are several BSRN sites around the world, as well as some mobile sites that they actually move around and put on islands or things like that. And these are kind of like the global benchmark for making radiation measurements in the scientific community. And one of the things that this group that got together to put this document together was working on is trying to figure out how can we make these measurements on platforms at sea at the same kind of quality and as is made by these BSRN land stations. We're trying to make a global network of these radiation measurements. So the document's available if you want to see all the gory details and all the people that were involved in this, you know, from the scientific and other communities. I recommend you take a look at the full paper. Next. So why do we care? You know, here we're going to focus primarily on shortwave and longwave radiometers, particularly the component of radiation that's coming down from the sky. So what we think of as downwelling radiation. But the key thing is the radiation is like the player for understanding the atmosphere-ocean energy balance and energy budget. You know, we get all the heat on the Earth comes from the sun, so that's where it starts. So we have to measure what's coming in, how much of it is getting absorbed, reflected, you know, et cetera. And I'll show a quick diagram here in a second. But in terms of the user community, it's very diverse. The one big community is a community interested in the exchange of information between the ocean and the atmosphere. So that could be exchanges of heat, water, chemicals, aerosols, all these things that exchange between the ocean and the atmosphere rely on that radiation balance and that exchange of temperature and energy into the ocean and out of the ocean. Of course, there's a number of satellite developers. People are launching things into low Earth orbit. Almost all those satellites measure something like a radiance of the Earth, and you have to be able to calibrate these sensors, and the surface radiation data is a key player in being able to build those retrieval algorithms that they use for space-based platforms. And then, of course, modelers, people that are modeling various aspects of the energy budget. They need ground truth. They need something to work from. And for those of you that, obviously a lot of you, I'm sure, have been on biology cruises, process study cruises, chemical cruises. The radiation data often plays a role in those process studies, especially the biology, when you're thinking about, photosynthesis and the planktons in the ocean. Next slide. So as I mentioned, it's complicated. What goes into the energy budget, there's a lot of things going on. So in the dark yellow on the left side, you see the energy coming in from the sun. That's the shortwave radiation that's coming in. And a lot of that is absorbed by the surface of the Earth. Some of it's absorbed by the atmosphere. Some of it's reflected by the atmosphere, reflected by clouds. Reflected by the surface. If you're someplace in the polar regions where you have a lot of ice, a lot of this energy just gets reflected. It doesn't actually get absorbed by the surface. And then on the other side of the equation, you have what's going out. What's once the energy is absorbed by the surface, some of that is being radiated out, and that's long wave radiation going out from the surface of the ocean. But there's also long wave radiation coming down to the surface of the ocean. Where does that come from? It comes from two main sources. It comes from the water in the atmosphere and the clouds in the atmosphere. Those actual water droplets actually absorb some of that shortwave radiation coming in, and then they emit it out as long wave radiation. So the primary places you're getting the long wave downwelling from are from the atmosphere itself, the component gases of the atmosphere, and then clouds and water vapor in the atmosphere. Next slide. So what does the data look like? In this case, what we're looking at is shortwave radiation. This is the downwelling shortwave radiation on a clear sky day and a cloudy sky day. The red curve is an ideal clear sky curve for the location of the ship on the day it is making these measurements. This ship happened to be operating in the tropics on the day these measurements were made. On a clear sky day, you can see that radiation curve is fairly smooth, kind of a bell curve, tends to peak out in the 1,000 watts per meter squared kind of range. Though it can be higher, you can get values in like the 1500s, especially on days that are partly cloudy, because there what you're seeing is a combination of the shortwave coming down directly, but also what's being reflected off bright clouds. So you can get these peaks, these spikes in the shortwave radiation on partly cloudy days. On a cloudy sky day, of course, the more clouds you have, the less solar radiation you get coming in. Also, it's dependent on time of year, latitude, if you're in the polar regions near the winter, shortwave radiation really low. If you're in the tropics in the middle of summer, very high. The bottom is the long wave radiation. And on these same 2 days, you'll notice that in the clear sky situation, the long wave radiation is pretty flat. You don't see much change in the long wave radiation over the course of the day. And again, this is because this was in the tropics. In the tropics, the atmosphere is so moist. There's so much moisture in the air that almost all that long wave radiation coming down from the atmosphere is just coming from all the water vapor in the air. And so it's a very constant atmosphere. It's a constant humidity. So you have fairly constant radiation. Partly on the cloudy sky day, you see a little more variation in the long wave because the clouds are emitting that long wave radiation. So you get a little more long wave on when the clouds are there. But that variation is much bigger if you're in like a mid-latitude drier environment. If you're in a drier atmosphere, you'll see much more variation in the long wave radiation when there are clouds. The clouds are the big contributor to long wave radiation in a northern latitude or a high southern latitude. Because there's not as much moisture in the air itself to give you long wave. It's the clouds that give you that signal. Next. So when it comes to sensors, to measure these, what are the common sensors that we can put on a research vessel to make these measurements? The two big ones are measuring that direct incoming shortwave radiation using a pyranometer, and the incoming long wave using a pyrgeometer. So these are basically measuring that part of the radiation that's that big piece of shortwave coming in and big piece of long wave coming in. Another sensor that we can put on a ship, which is fairly easy to use, is what's known as a diffuse shortwave measurement. In like a BSRN station on land, the way they measure diffuse radiation, basically they have a shadow band. And so what that does is it blocks the direct sunlight because there's a shadow or a band blocking that from the sensor. And all you're seeing is what's kind of diffuse coming around that shadow band. The problem with those is they have to be sun tracking and they have to be very stable. You don't have that option on a ship. You have the ship's always moving, so you can't really use one of these shadow band radiometers on a ship very easily. So Katie's going to show you an example of a sensor called the SPN1. It is actually designed to do direct incoming shortwave and diffuse shortwave using a single sensor that has its own kind of built-in shadowing systems in it, so that you get those two measurements without having to have this sun tracking kind of sensor. Then another component we can do on ships is we can actually measure that upwelling long wave radiation. And the way we do that is by using an infrared sea surface temperature sensor. If you use an infrared sensor looking at the ocean, you can actually measure that outgoing long wave radiation by measuring the temperature of the surface of the ocean. These are not very common on ships yet. The Sikuliak has an infrared Hytronics infrared sensor, and there's some very high-end things like the Rosser, the ISAR, and the Mary. These are $50,000 instruments that can measure this. Those are what's used by the satellite calibration community for sea surface temperature. They're kind of the gold standards. But there is a move in the community to try to develop more lower cost infrared sensors for measuring that upwelling ocean temperature. Next slide. So in terms of sensor selection, how do you decide what sensor you want to put on your ship? And one of the things that's in the paper that was developed by the community is this decision tree. I kind of just walked through this decision tree thinking about from the perspective of a research vessel. Okay, so you start at the top, and the first question is, does your platform have a mean tilt, or is it frequently tilt 2 or 3 degrees? You have to understand this decision tree was designed not for ships, just for ships, but all for platforms, buoys, fixed stations or towers out in the ocean. But you can figure, yes, okay, a research vessel is more than likely going to tilt at some point. And it's more than likely going to have a mean tilt depending on how the ship's ballasted when it's out at sea. So you're going down this yes kind of road. And then the next question is whether or not you would have a stabilizing platform. So there are platforms you can put on a ship that will make sure that your radiometers stay level as the ship tilts. They're very expensive, they're rather finicky, and they're really only practical for a single research cruise, like something that's specifically trying to do this really high resolution radiation work. So it's probably not practical to have one of these stabilizing platforms on every cruise that you do. So then we're kind of following down that no pathway into the middle and say, what do we want? Is it the highest quality measurement a priority, or is cost a priority? And I'm going to say, okay, NSF can afford the highest quality measurement. And so we're going to go for quality, not cost. So then we get down to the final decision. What should be deployed for shortwave measurements on a research ship is a combination of the SPN1 to do direct and diffuse radiation and a Class A pyranometer. And if you're wondering what a Class A pyranometer is, in this paper, there's a whole list of the manufacturers that make Class A pyranometers. The most common ones are that you're probably familiar with are Epley, which is, I don't know if they're anymore, and then Kippen-Zonen, which is what Katie's going to show you, some of the Kippen-Zonen sensors. Delta T is the one that makes the SPN1. And then there's a couple other companies that I'm not as familiar with, which I believe are European companies. But some of the things you're trying to look for is some of the things that you want to do is minimize the thermal infrared offsets when you're deciding what sensor to use. And ventilation does actually help with reducing that with these sensors. Next. And then there's the long wave sensors. The long wave sensors, again, there are multiple companies that make them. One of the things that's worth noting here is the shortwave sensors. There are a lot more industry standards for shortwave sensors because the solar power, solar energy community is driving that. For the long wave sensors, there really isn't as much standardization. So this is one of the things that this community of best practice folks for radiometers is really trying to help define. But again, the ventilation of these sensors does help reduce anomalous heating in these sensors. And one of the things you have to think about with infrared sensors is what's around them that can be emitting long wave radiation. You don't want these sensors next to a lot of structure because the structure of the ship heats up and can actually influence these radiation measurements. Next. So at this point, I'm going to pass it to Katie and give you an opportunity to take a look at some of these sensors. And then we'll come back and go through some other things.
So
Any
Shawn,
questions at this point?
Any questions so far? Hi, Ethan.
Hi. Thanks, Shawn, for the talk, and thank you so much for mentioning skin temp measurements. I just want to add to that, if folks are interested in that measurement, the lesson that we learned in the last year was that you cannot do it alone with a CU radiometer because you need to take out the effect of the sky. So if you want to collect scientific grade skin temperature data, we need to also have a sky viewing radiometer to compensate, do that background compensation. Then you'll get good skin temperature.
Yeah, and that's one of the nice things about the Rosser unit is it has an internal black body calibration target. So it actually is able to account for that. If you just have the Hytronics, you're gonna have that issue.
Yeah, and it's
50K and
We
a
did
company
our-
that may not really exist.
yeah, I was going to also comment that, and I couldn't quite hear Ethan, but it is actually even more complicated on a ship because with those infrared thermometers, one of the key things is you have to be very careful about the field of view they see of the ocean. You want to, and you need to make sure that they are not catching like the ship's wake. They have to look past. That's why they try to mount those way forward, so they're looking out forward or of like the ship's bow wake, because that can always affect the measurements as well. And there are folks that are working on algorithms that utilize like I wouldn't say GoPro, but they actually utilize cameras to actually see what, in real time, what's the sea state, what's the sun glint, all these kind of things that can affect those infrared measurements and correct them.
So Eric had brought up the roster, Shawn, and I'm not sure in terms of support, and I'm not sure if you've heard anything lately. There was a campaign of sorts to get that to be continued, like to get people to support it. I don't know.
Yeah, the last I heard was, and I forgot the gentleman's name at UW, Andy Jessup, I think it is, was looking at potentially supporting maybe existing rosters. I don't know if there'll be any new builds, but and then again, I mentioned there are two other systems. One's called ISAR, which is built by the NERC in the UK. So the national, their research council builds them in Southampton. And then the Mary, which is a very high-end system that I think is the University of Miami. But again, I don't know how many of those have ever been built. So.
And Ethan has a question.
Sorry, I'm just.
No, go ahead.
So Andy is contracted to build a roster-like system for the RCRDs. He's trying to get a grant to support that operational. That is the scope.
So they've already been built and delivered. It's probably just support at this point, hopefully.
It is not supported, but that is like the last of the roster.
Yeah.
Well,
As of now. So Shawn, I already kind of sent the Delta SPN1 around, and I just want to show everybody. I'll give you guys some time at the end too, because we have some more slides to give. This is one of the paranometers, the SMP. I think this is the 21. I borrowed this, and you can see it's got the ventilation fan too. So when Shawn was talking about how it's nice to have the ventilation fan for a few reasons. One, it can reduce the thermal offset. So anytime you have sun beating down on this sensor, if you have heating of the dome, it can affect the measurements. So the one nice thing about this is it will push air up and over the dome to kind of keep it cooled down. The other thing, which I was going to ask Ethan about, is whether or not it actually reduces maintenance requirements. If it does reduce dust and certain things settling on top of that dome. Because I think Sukuliak's had them on board now for a couple years.
I think that's a great question.
What do you guys think?
I would say, yeah, I still tend to, wipe it off with a Kim wipe every so often. And the ventilation unit, it does have a filter in there. And so we do have, so it's on our monthly PMs that we replace that filter once a month.
So
there is a design flaw with the filter that we found that it's very wet with just rain, and so during the Arctic region, feel that.
Yeah.
So Katie.
Go ahead, Shawn.
Katie, I was just going to follow up on that question. Another group, I don't know if anybody's there from the Healy. The Healy is currently running both Epleys and the Kippenzones on their current Arctic work. They've been running them in parallel this year. And we're getting both the data sets through SAMOS. And I have not noticed, I've noticed hardly any difference between the shortwave radiation, but there is a subtle difference in the long wave. And I don't know if that has to do with the one having ventilation, the Kippenzonans being ventilated versus the Epleys being not. So.
I think there was also a difference in the dome design in terms of the light that they allowed to penetrate through. Ethan has some comments. Hold it. We do need a punch card for you. Right?
So the problem with the Epleys in polar environments is they do dome temperature correction. And Epley never designed it to work below -2C. So it's the opposite there. If you're working below -2C, you will not get good values out of that unit. If it's warmer than that, then yeah, it should be fine. The way they designed that dome, there is no correction.
For the
They eliminated that.
for the SGR.
So
So I'm going to pass this around. It's kind of heavy. But I think David passed it. No, it's okay. Yeah. If you break it, it doesn't matter. It's not mine. Great. Yeah. So yeah, watch that top. Yeah, you can take it off. Again, that's not mine. That is really gross. And I'm gonna tell them like, really, you send me a demo unit and it's like covered in dust. This is what it should not look like. Yeah, I'm gonna pass that around. You guys can kind of have a look. That again is the SMP. So Shawn, I don't know, do we have any other questions before we move on? Because we actually have some more slides. Is everybody in the fleet kind of moving towards different radiometers since Epley's not necessarily supported?
So we're looking at, we don't know, we're purchasing the zones yet, just in terms of like funding.
Yeah.
We currently have Epley's and we have the rad boxes that were supported by our RMR kind of, which definitely doesn't exist.
Yeah.
And actually some weird phone calls. And yeah, so I'm kind of at the point of like, I talked to Epley because they're like right down the street from us. So I walked in and brought the box in and said, what do I do with this? And he's like, it's probably fine. And it's like, for how many years can we just say it's probably fine? Yeah. So that's, yeah, the conversation.
Yeah, I know there's been a huge shift. A lot of people moving over to the KIP and zonins. That's what we're doing with it now too. But yeah, RMR company was the same company that made the roster.
Oh.
Yeah, so they make the roster and the DAC units for
Yeah.
the Epley's. Yeah, it's kind of a bummer. All right, Shawn, I'm gonna let you keep going. I'm just passing the radiometers around.
Sure. Okay. Yeah. Next slide. So when it comes to radiometers and where do you put them on the ship, location matters. It's probably the biggest thing. So these are just some recommendations for location. Get the sensors as far forward and as high as possible. You obviously want to be avoiding things like your exhaust stacks that can get soot on them. But the other thing that's really important, and I know it's a cost thing, but redundancy does help. And that's what this graph or this plot is showing. What you're seeing is a ship that has a port and a starboard shortwave radiometer on board. I don't really know exactly how far apart they were on the ship, but the blue curve is basically what you're seeing is all those dropouts are shadows. It's when a mast is shadowing or something over the course of the day. So if you can have redundancy, a user can actually go in and correct out, the shadowing issues, by using both sensors. Leveling of the instruments is really important. You wouldn't think, you might think making it level doesn't matter on a ship because the ship is moving, but one of the things that the users often need to do is actually correct the radiation measurements for the mean tilt of the ship. And so if you make sure your radiometers level with respect to your ship, then they can use the high resolution motion data from your ship and your tilt data to actually correct if the ship's, got a mean list or a mean tilt because of the way it's ballasted for the cruise. So, and then the last one is the electromagnetic interference. Radiometers are very susceptible to the EMI. And so whenever possible, you want to keep them away from things that produce that. And even better, if possible, if you can do an EMI survey of the vessel. And that's something that I know they're doing with the new builds, like the RCRVs. Get somebody to come out and survey where that EMI cloud is, so you can get the sensors in a good location. So next slide. Of course, location, operational reality check. Location is always a trade-off between the best location for science and accessibility. Can you actually get to it to do what you need to? So this is just it's a plot of the Skuliak, of course, a schematic of the Skuliak, but you can see the letters on here. I'm just going to give you an opportunity to just make your suggestions. Where would you put the radiometers, based on the lettering on this ship? What would be your first
Raise your
choice?
hand. Okay, we got one for A, Shawn.
Okay.
What about B? None for B. C? Okay, so 1 for C.
Mhm.
Let's see. We're gonna go F. How about F? Anybody for F? All the way at the top there. Who wants to service that one? Oh, I got 1 for F. Okay. Penalty pay. I love it. How about H? Okay, 1, 2, 3, 4, 5, 6, 5.5 votes for H. And then G. How about G? Yeah. Okay, 2 votes for G. So I think the winner is technically H. What do you say about that, Shawn?
Okay, so the answer would be H is great for access, terrible for measurements, because it's after the stack. So you're going to spend a lot of time cleaning it. Unless you're going out and cleaning it every day, you're not going to get reliable measurements from that location. F and A are the best for science, but as you noted, F is not necessarily accessible depending on how that mast is designed, on a given ship. So I would say F, A, and G are probably the best locations. C is not bad. That's kind of the middle one, but what's the other issue with C? That one's probably going to be in your EMI cloud. You're really close to your radars and stuff. So that might be an issue with that location. So yeah, and every ship's going to be different, but keep with the rule of thumb of trying to get it as far forward on the ship as you can and as high as you can get. But obviously you have to put it someplace you can get to it, to clean it, maintain it, etc. Next slide. So what data do we want to record? I'm not going to read through all this, but this is just kind of the basics. It's all in this document of the information you want to measure and store. Obviously, whatever data message comes out of that sensor, you want to capture the whole thing. You want to make sure that that's in your raw data that's going into R2R as opposed in the post-cruise distro. I think it's really important to emphasize that if the sensor has diagnostics, capture those and you take advantage of them. The KIP and Zonins are one that I believe do have sensor health diagnostics that come out of them. So certainly a valuable thing to have. And then not so much for your day-to-day work, but for the science, the people that actually really care about this data and really want to, correct it for all the tilts and all the other things, if you can record the vessel motion at least the sampling rate of the radiometer, higher if possible, that's kind of the recommendation, because then they can actually utilize that to correct for all the tilts and rolls and all that kind of information. So right now in this paper, they recommend 1 Hertz sampling for both your radiation measurements and the motion, the vessel motion data. Next slide. What metadata to record? Obviously, you want to capture your serial numbers and all your calibration values and history. But this is what earlier on, if you were in the R2R session, Becca was talking about electronic logs. Very important to capture as much information as you can in an electronic log about when you have problems, when you do cleanings, when there's maintenance work done. All that stuff is valuable for the downstream science user that's looking at the data. In terms of sensor location, what's really nice to do is you always want to have a photo of the radiometers themselves and what kind of mast they're on and that kind of thing. But it's also really interesting to stand where the radiometer is and take 360-degree photos, or just take a video, where using your phone, so that you can see a user can see what's in the field of view of the radiometer itself. Is there a mast over here, or is there a bulkhead from the ship within a certain distance? Having that 360 field of view is really, really valuable for users of the data. And then of course, logging, whether you have bird deterrence spikes or ventilation, because those can affect the quality of the measurements as well. Next. For maintenance, the big things, and Katie will go into some of this as well, but one of the number one things, and that's what this photograph is showing, is pyrogeometers that were not well packed when they were shipped, and you end up with broken domes. This is one of the number one ways to do in your radiometer is how they're shipped and packed for shipping. A lot of these radiometers have desiccants in them. Some you can change yourself. Depends on the manufacturer if you can access them or not. But the recommendation is to at least look at those and potentially change them on a weekly basis or as often as possible, because moisture can really affect the measurements from these sensors. I'd say from the SAMOS project, when we've seen problems with radiometer data, I'd say 8 times out of 10, the problem with the sensor is a connector or a cable problem. It's not the radiometer itself, it's something going wrong with connectors or cables. So making sure you routinely check all that is gonna help a lot with data quality. And then of course cleaning. Here you always have that operational reality too, but the recommendation, and this would be to meet that baseline surface radiation network kind of standard, is to basically clean them every day prior to dawn. Y'all aren't going to have time to do that. So, a minimum would be ideally to do them weekly, make sure that they're cleaned once a week. But the reality is as often as possible. Ideally at the beginning or end of each cruise, they should be cleaned, because then you're going to get better quality data. Next.
Curiosity, how many people have radiometers on their ship right now? How many people clean them every day? How many clean them once a week? Okay, all right.
All right.
Clean them.
How many have ever cleaned them? Yeah.
That's it. Okay. All right. No judgment. No judgment. All right. We had one for each, Shawn.
Okay. Excellent.
Yeah.
I mean, I can speak to that, honestly. I've been on 6 NOAA ships, 1 that cleans it every day, and 5 that clean them never.
Yeah. Okay. Yeah.
For the one that's an everyday cleaning, where's the accessible?
It's brown, it's on a place kind of like G on the diagram.
Yeah.
Pretty far forward, but not on the map.
And accessible.
Yeah. On the survey rounds.
So Katie, I don't know if you want to go through anything at this point.
So, like I said, my alcohol got confiscated at the airport because apparently you can't fly with those things. But I just wanted to mention a couple things with cleaning. I do have an SOP that I can share with the group. And one of the things we're going to talk about at the broader session tomorrow is how people prefer to have these documents shared, because they should be living documents. We should be using them. We should be saying, this does not work. We need to alter this. Like, does anybody have any ideas about how we should share those within the community? It's okay if you don't.
As far as Google Docs, I mean, it doesn't. For all of our mapping operators on EX and beyond, we have Google Docs and make comments in real time edits. Temporize it. There's not really much of a paid stamp unless it's overall.
Yeah.
But it's like, oh, I tried this methodology, it works better. And usually somebody who's on board or times will make a change, eliminate the content.
Yeah.
But I like to have it be to identify date for every change. More than itself.
Yeah, we've really battled with Google too, because if we host it within NOAA, which we talked about, we're like, yeah, we'll totally host a space. Nobody else can access it.
Yeah.
So that's been a frustration too. Yeah, Gretchen.
For NOAA.
Yeah.
I always check there first.
So we have a document called Linkapalooza, and it basically includes links, thanks to Charlie here, or the name as well. That includes links to all of our SOPs and different resources in the community. We've also talked about the mapping, the wiki that they have would be good, really fantastic, and thinking about how we can post that in a broader environment.
So use GitHub and then
have someone be the point for change requests.
Yeah. This is what we're trying to push, maybe yourself or someone else to help kind of host something like
Yeah,
that.
that'd be cool to see.
Yeah.
In-house years ago, our text developed a wiki and some people on board, but take it
Yeah.
to the next level.
And that's all great, but I guess the important thing for me is having someone that change.
Yeah.
Like it's not just like an open, everyone can edit it.
Yeah.
Like
Yeah.
everyone can
Yeah, very
suggest.
important.
Yeah.
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 Yeah, so we have a host of these different SOPs that are available for different sensors. We have setup and configuration guides, we have data format guides, we have spreadsheets that talk about the ranges that you should anticipate to see with both raw and processed data. And we have what we call standard operating procedures right now. We're trying to move away from the word best practice because it's hard to really like label something as a best practice. It actually should be certified a best practice. It should be out in the community and used for a while before you can actually call it that. So we have a bunch of SOPs that are now like battle ready, right? Like we need to get them out in the community. We need you guys to give us your feedback and say, yeah, this works, this doesn't work. Hell no, I don't have time to do this every day. Like it just, what is reasonable? So with these sensors in particular, they're fairly low maintenance. So with the ventilation fans, like you saw, it's really just cleaning the body down, and I'll share the document with you so you can kind of go through it yourself. But it's really just keeping the body clean. Sometimes these fan units go out, but you should have field replaceable spares with you. They're pretty easy to replace. And then, like they said earlier, there's a filter on the bottom. So you should change that, especially depending on your operating environment. You might need to change that more than less, especially if it's early. And even a humid environment, I haven't heard that before, like this. I don't know how many times you guys have had these fail. Have you had them fail at all? They're pretty robust. They changed the fan units a while ago, probably a couple of years ago now. I think this is actually an old one, so that I think they're a little bit more durable.
When you say failure, you talking about fan failure or something?
Yeah, it does look a little bit. That's really all it is.
Do you often see that much dust inside the?
No, I was
just
so
curious,
embarrassed.
that's cool.
I got it here and I opened it up and I was like Kip and Zoe gave me this to show you guys. I'm like, oh gosh. So this is what it should look like. You should really, yeah, it's fun stuff. So yeah, it should be a little bit. Yeah. So for the unit itself, these domes are pretty hardy. If you ask any optical scientist, they will shriek at you if you say you use a Kim wipe on these. You should use lens paper on any optical case. For these, though, I think it's perfectly acceptable to use a Kim wipe. Usually, just washing them down with a bottle of fresh water, out water, and then if they are really dirty, for breaking out the isopropyl, don't scrub. Just don't scrub. Stab. A little dab. And if you do end up having to really like scrub, which hopefully you don't because you're cleaning it more than once, in a decade, then, just try not to. If there are particles that you can like really see on there, try not to scrub it because you don't want to scratch the glass. Otherwise, like I said, they're pretty darn dirty. So once a day, like Shawn said, is what the VSRN gurus would tell you to do. But really, honestly, as often as you can. It does make a difference. And Shawn, I think, is going to show some examples of troubleshooting and some what kind of bad deals. Like, yeah, Justin.
So you talked about like motion of the ship affecting it and stuff. For those of us with like a pause, is it just going to be tied into it when it like gets to SES?
You can if you have a monument nearby, like if you can map it to there. Yeah, and unfortunately that's something that we're trying to push on the NOAA ships is actually having a reference system.
And
it's a work in progress.
would you recommend us like already getting Pelican cases for like when they arrive?
I think they'll be delivered with all of those. Yeah. So I got you guys covered. All of that got shipped this week, so it's gonna be exciting. All right, Shawn, I'll let you take it away with calibration and your troubleshooting.
Okay, yeah, just a few more slides to go through. Obviously calibration is always a question. Everybody asks how often should they be calibrated? And again, from this working group, the recommendation is that these radiometers are calibrated every 1 to 2 years. And of course, the calibration is generally done by the manufacturer. But there's kind of another question for the RV tech community is, are there other facilities we can use to calibrate these sensors? And some of the larger operators, I think like Scripps and Woods Hole might have their own calibration facilities for that they can calibrate some of these radiometers. I don't know if there's an opportunity for other operators to leverage some of these regional centers, but something to think about and potentially discuss. In terms of the standards, and they are documented in this paper, shortwave radiometers are traceable to a world radiometric standard. So you want to make sure your calibration lab is doing that. And then long wave to a world infrared standards group. So that's just when you're checking with the facilities to make sure they're using the worldwide standards. The shipboard radiometer community itself is still trying to develop standard calibration procedures. There are no real good procedures set in stone for shipboard radiometers. There's more for the land station based radiometers. But that's one of the next things that this kind of working group that worked on this paper is going to start looking into. Next. One of the things that you all can do, obviously, is monitor the data from the radiometers, and just a few things just to mention that you can keep an eye on. Shortwave radiometers routinely have a nighttime offset that is generally negative. Shortwave radiometers tend to go slightly negative at night. It shouldn't be more than a couple watts per meter squared for the newer radiometers, like a Kip and Zonin. The Epleys can get down to as much as -10 for the offset, and that's fine. If you see them at -15, -20, something's wrong with the radiometer. In terms of plausible ranges, again, I mentioned short waves, usually between 0 and 1200 watts per meter squared, but can be as high as 1500 on partly cloudy days. Long wave radiometers, 40 to 700, much higher in the tropics, generally in the 400 to 500 range in the tropics, but lower in the drier, kind of atmosphere of the higher latitudes. And then I mentioned, obviously, the clouds affect the more so in higher latitude, drier conditions. You can compare to climatologies. I actually got these recently. We even doing our quality control don't use a day-to-day climatology for radiometers because there really aren't many out there for long wave and short wave. But these are two. I just put the links in here. One is a monthly data set, and another one is a daily data product. And so these are good for doing just kind of really broad checks to make sure that your radiometer is in a reasonable range. The thing to note is that, of course, these are going to damp out the diurnal signals. So they actually, you can see like the shortwave one goes up to 300 watts per meter squared or 360. And that's because it's averaging in all these days. So those daily peaks get basically taken out of them in the data set or in the climatology. So last but not least, just going to go through a couple examples of suspect data from radiometers and the causes. So this one here was from, again, data we got from one of the ships through SAMOS, and it's long wave radiation, -700 watts per meter squared. Clearly there's a problem. You can't have negative long wave radiation, and certainly not that negative. But this is where understanding the content of the data message coming off the sensor, whatever it is, through using the user manual, is really important. Because in this case, the situation was, this is an Epley sensor. It has a case and a dome temperature. And those two temperatures were about 40 C different from one another. they should be really close to one another. If they aren't really close to one another, it basically means you either have a compromised thermistor or a compromised dome is the most likely cause in this situation. So this radiometer would need to be sent back for repair. Another example, this is shortwave radiation, and you can see the sunset and sunrise time on here. I'd mentioned earlier about this offset where these shortwave radiometers will go negative at night. Well, this one here has got 50 watts per meter squared positive at night. And the first, you were scratching your head going, okay, that doesn't make any sense, until we talked to the operator. And this ship happens to be a fishery ship that's doing nighttime trawl work. And they have these massive bright halogen lights on the ship to do their nighttime trawl work, which of course is giving you, artificial shortwave radiation. We've also seen this situation when a ship is in a shipyard, sitting in a port with a lot of bright lights. You can also get positive nighttime. So this would be an example of something that would be good to make a note of in your electronic log. If you happen to be doing trawl operations at this time, so people know that that's why they're seeing, positive nighttime shortwave radiation. And last but not least, bird is the word. So a very common problem on ships is birds sitting on your radiometer. And this is an example on the bottom graph, or the bottom two graphs. You can see shortwave and long wave. The short wave's telling you it's nighttime. The long wave's telling you you got a bunch of birds spending the night roosting on your radiometer. Yeah, so we've seen this on probably a half dozen ships, primarily in the tropics, but I'm sure, where there's a lot of tropical seabirds. But it is definitely a problem that'll crop up, I think, on most ships at some point or another. So again, another thing that's, if you happen to see them and you notice them, make a note in your e-log so the user, can say, okay, that makes sense. That's why I'm seeing this weird radiation data. So that's all I had. We'll open the floor for more questions.
Yeah, Eric.
I have 2 questions today. All right, I'm kind of fascinated by heat tilt. I wonder if there's a kind of a generally accepted way to calculate that when we have the capability to give you instantaneous tilt.
Yeah, so did you hear that question, Shawn?
I only heard something about mean tilt, but yeah.
Yeah. He was asking about mean tilt and whether or not there's
Is there a generally accepted way to estimate that?
a generally accepted way to estimate that.
So I didn't put it in this, but in the paper, the full Frontiers paper, there is a whole section on tilt and tilt correction. So that would be, I don't have the details on the top of my head, but there is information in there, I believe, on how to do those calculations and do those corrections.
Did that answer your question, or
Yeah, that's great.
you said you had 2?
Yeah, part data. Is anyone actually using the kit? The gist of my question is Zona does not offer an intermediate option. What version they bought now?
I think most people are buying the S's, not the C's, like the SMPs or the SGRs, the smart, not the analog. Yeah. And probably Modbus.
Software.
Yeah, that would imply to write a driver for it that has.
Yeah, I know at least with our CRV we did Modbus. Is that what you guys do too?
Yep.
Yeah.
So, you talked about the lights affecting it at night, for those of us on fisheries vessels that are going to have that constantly. Is there a generally accepted way to negate that, or is it something we're just gonna have to put in comments like during this time zone?
Just gotta put it in the comments, yeah. As long as we have a record in the data log, then, poor Kristen's not looking at the data and like, God, what's wrong with this ship? And just so it's part of the metadata record, so then people who use the data in the long run can look at that and say, oh, okay, that was due to artificial leg.
Yeah, I heard the question about how to mitigate that. Obviously, the other question is, where is the sensor? If there's another option to put the radiometer someplace else on the ship where they're less affected by those trawl lights, that would be the other solution.
Are you guys after the stack? Is it in that area just aft? Oh, I know that, yeah. But before, was it located in the? Yeah. Any other questions?
On the Healy, we have our, not after the stack. And we're just wondering if there's any quality of data noticed.
So this is with regards to the Healy, and it might be a better question for Kristen. Does Kristen do the Healy? Or do you, Shawn?
Yeah, I'm the one that looks at the daily Healy
Go ahead.
data.
They were saying that they are located after the stack and have been for as long as they can remember. They have the Epleys and the Kippenzones. Have you noticed any issues with data quality?
Well, it's an interesting question. In the data we receive, it's fairly hard for us to tell whether those sensors are getting dirty over time without, if the sensors are cleaned, we'll see the change, So without some kind of, we usually don't get a note or anything when at least from the Healy, we've not been getting information when the sensors are being cleaned. But I do suspect that they're going to be more, get more buildup being after the stack. So, and it's even more complicated on the Healy because of her operating environment. You also have to deal with the fact that they'll get frost on those domes as well. And whether or not that shows up in the data noticeably or not. Sometimes it does because you get, enough daytime sunshine on them that you see it melt off. So, yeah.
Do you guys have vent fans on the Kippenzones?
I'm also curious about just after the stack.
Yeah, did you hear that, Shawn? Do you notice anything with the heat and exhaust in the radiation data? Any impact?
I can't say that, I can't say specifically for the Healy. I have seen it on some ships where depending on what the ship relative wind angle is, and you can actually see the stack exhaust plume go across, the radiometers. You can actually see some dropping of like shortwave radiation and particularly increases in long wave in those situations. So you do see steps in the data when the stack plume goes past these sensors.
I'll try to find that and share that with you. Any other questions? Yeah.
Go back to the slide with the paper.
Oh, yeah. And we'll hopefully have these slides for you as well. A really long paper. Yeah.
I have a lot of people around.
Yeah. A lot of voices. Any other questions? All right, we are at time.
Yeah, I want to thank everyone today. I mean, I know there was a lot of shuffling around, especially at lunchtime, and I appreciate everyone's patience since we got the room set up. We have a couple announcements. The buses are here, so if you would like to get on the bus, you can do that. Also, remember the reception tonight is at the hotel, the Sheraton, in the Harbor's Edge room from 6 to 8. So light tapas and a cash bar. So I hope to see you all there because I'd really like to talk with you. I feel like I haven't really had a lot of one-on-one interaction. And so anyway, that's my spiel. But thank you, Shawn. Thank you, Katie.
Thanks, Katie.
Thank you, Shawn.
Have a good night.